Welcome! It's already the last lesson of Math2. And in the linear algebra part, we're going to talk about one more new subject, which is called the cross product. And in the languages part, we're going to look a little bit more in depth in how to convert a graph into a finite state automaton. So let's start with the linear algebra part. If we look at what we've learned the last lessons, then we were talking about lines and planes, and we could say draw conclusions about those lines and planes. For instance, question A, is the line L parallel with the plane V? Okay, how could we figure this one out? If we look at parallel, it means that we have to look at the direction vectors. So the direction vector of L is 5, minus 1, 2, and the direction vectors of the plane are 3, minus 1, 1, 2, 0, 1. And when are these line and this plane, when is this line and this plane parallel? When the vector of the line is depending, can be built with the help of the other two vectors. So let's check this. So 5 minus 1, 2. Is that depending? Can it be built with something times 3 minus 1, 1 plus mu 2, 0, 1. Okay, well, if we choose lambda being 1 and mu being 1, then immediately we see that 5 equals 3 plus 2, minus 1 equals minus 1 plus 0, and 2 equals 1 plus 1. So indeed, the line and the plane are parallel. By the way, if you don't see this solution immediately, we just have three equations with two unknowns and you can solve it with all the knowledge we have so far. Second question, does line L belong to the plane? Okay, then we have to look at the starting point. So is this point which is on the line L, is this also on the plane? Okay, let's see. So 1, 2, 0. Would that belong to the plane? So can we find a lambda and a mu in such a way that we can solve this puzzle? Okay, now let's look at it. So we see if I look at the y coordinate, then we see that it's 2 equals 1 plus lambda times minus 1. So if we choose lambda minus 1, then we have this 2 in order. Let's look at the other ones. So then we have 1, the first one, x coordinate, being minus 1, minus 3, plus 2 mu. So that means 1 is minus 4 plus 2 mu. So that would give us mu being 2. Okay, then we only have to check it in the last one. So is the z also correct? So 0 would be 0 minus 1 plus 2. Okay, now we have definitely a problem because 0 is not equal to minus 1. So the line L does not belong to the plane. So parallel, yes. Belong, no. Because the point from the plane from the line is not on the plane. Okay, also we've learned something about the coefficient vector. So if we start with this equation in 2D, then the elements in front of the x and the y are called the coefficient vector. So 5 minus 2 is the coefficient vector. And hopefully we remember that the coefficient vector is perpendicular to the direction vector. So how can we find the vector form of line L? Very straightforward. We just need one starting point And then we need a direction vector which is perpendicular to the coefficient vector. Okay, let's start with the last one. Perpendicular to the coefficient vector would mean switch the numbers. So the 5 will go below, the 2 goes up, and make one of the signatures different. So in this case, I've chosen to change -2 in +2. Then to find a starting point, we'll just have to look at the equation and find one easy starting point. Okay, 1 springs to mind. That is 1, 1. 5 times 1 minus 2 equals 3. So in no less than 30 seconds, we found a vector form of a line given by a specific equation. We can do the other way around as well. So if I have a vector form, how can I find the equation? So again, coefficient vector is perpendicular to the direction vector. So a coefficient vector of the equation would be switch the numbers and make one of the elements with a different signature. So -3, I've made 3 and 1 stays 1. So apparently x plus 3y equals a value is the equation of this line. So now we only have to fill in one point on the line to find the value. Okay, we have a point. That's 3, 2. So x plus 3y becomes 3 plus 6 equals 9. So the equation would be x plus 3y equals 9. In a 3D situation, it's a little bit more complex because now a vector form has two direction vectors. But it's not a big deal. As long as we remember that the coefficient vector is perpendicular to both direction vectors. So it's perpendicular to direction vector 1 and direction vector 2. Okay, how do we find a vector perpendicular to this original coefficient vector? Well, a very simple trick is choose one of the three items 0. And let's take the middle one. And then in fact you have brought this 3D vector back to a 2D vector. So now we do the same trick as we did before. We switch the elements and of one of the two we change the sign. And this vector is perpendicular to the original one. And let's try it. So let's do the dot operation. So that would give us -5 plus 0 plus 5. And indeed, it's 0. So -0, 5 is a perpendicular vector. Okay, so if we look at the vector form, we just have some point on the line. Let's look at that one later. First direction vector. And now we find another direction vector. And again, we repeat the same trick. So make one of the elements 0 and switch the other two and change the sign. So these are two independent direction vectors. Note that the 0 is on different spots, so the vectors are definitely independent. Okay, what's left is that we need to find a point on the plane. Well, let's look at the equation again. Then maybe if we choose y being -2, then I already have 4. If I have z is 1, then I already have 5. So then I choose for x 0. So now we have a very nice vector form of the plane V. The other way around, it's a little bit more complex because now I have two direction vectors. So I have -3, 1, 4 and 1, -1, 4. So how can we find one vector which is perpendicular to both? I cannot just choose a perpendicular vector to, for instance, the first one. Let's take this one. So do the trick. Then this one is perpendicular to the first direction vector, but definitely not perpendicular to the second one. So let's check that one. Times 1 minus 1, 4. So that would be minus 4 minus 4 would be minus 8. So not perpendicular. So we need to have another trick. And this other trick is the last part we are learning in this linear algebra part, that is calculating the cross product of two vectors. Cross product of two vectors will give us a perpendicular vector perpendicular to both of the used vectors in the cross product. But let's first look at how we need to calculate that one. So if we have two vectors, a1, a2, a3, and we need to make the cross product with another vector, we can try to remember the formula, which is given here. So A cross product B should be this calculation, but I'll teach you a very small trick to remember it more simply. We'll just draw a small line here and we repeat A1 and A2 and B1 and B2. Now to get the element on the first position, I will do the determinant of the 4 elements below this first position. So the determinant of A2, B2, A3, B3. So that would give us A2, B3 minus A3, B2. Let me erase this one. So the first element is A2B3 minus A3B2. And see, that's exactly the one in the definition. Okay, for the second position, on the Y spot, we'll just draw a rectangle underneath the A2B2. So I'll take another color. So we'll draw a rectangle like this one. And now you see why I added A1 and B1 underneath, because now again I have a determinant. So the second one is A3 B1 minus A1 B3. That's exactly the one as given in the definition. And of course for the last one, let's make another color again. So for the last one, we go one bit lower and we use this rectangle. So then we get A1 B2 minus A2 B1. So we don't need to remember this formula, just remember that you use the determinant, and every time when we calculate on the first position, we use the determinant of the two underneath.